Let us discuss about the efficient way of calculating the DFT. This is accomplished using a set of algorithms which is called as fast Fourier transform. The method is called as fast Fourier transform because it is a more efficient way of calculating the DFT in comparison with that of the direct method. This is possible through reducing the number of complex multiplications and complex additions. The number of arithmetic operations performed in the direct method is more compared to that of FFT method. Hence, FFT method is considered to be more efficient. Now, let us start with the equations of DFT and IDFT. The application of the formula and getting the results is known as the direct method of calculating DFT and IDFT. Now, from the above two equations, we observe that the direct computation of x of k or x of n will involve n square complex multiplications and n into n minus 1 complex additions. For a complex valued sequence x of n, the n-point DFT may also be expressed as x of n is equal to x of r of n plus j xi of n. We are breaking x of n into its real part and imaginary part. The value of xr of n and xi of n are real values. Therefore, once the input is a complex valued input, the application of this complex valued input to the formula will yield the real part of DFT given as xr of k, the imaginary part of the DFT given by xi of k. We observe that the summation will have two terms. The first term here has cos, the second term has sine. The third term here is sine and the fourth term here is cos. Now, if we calculate the direct computation using the above shown equations, then it involves a total of 2n square evaluations of trigonometric functions, which can be easily verified because this equation will have totally n terms. Every single term will have one cos and one sine. So one term evaluated will have two trigonometric functions. Like that, there will be total of n terms in this summation. Therefore, the answer is 2n. Now, this is for a single value of k. In total, there are n values of k. Therefore, the value 2n has to be multiplied with n and we get the answer as 2n square. Coming to the second equation, the sine and the cos is already calculated in equation 1, so we need not calculate it a second time. So the total number of trigonometric functions which we calculate remains as 2n square. The number of real multiplications is said to be 4n square, which can be easily tested because here number 1, 2, 3, 4 can be counted as 4 real multiplications. Like this, there are n terms in the equation. Therefore, we can say it is 4 times of n, and this has to be evaluated for n different values of k. Therefore, the total number is 4n square. On similar lines, we can evaluate the number of real additions to be 4n into n minus 1. The number of indexing and addressing operations are also involved. Hence, in conclusion, we can say that computation of DFT and IDFT is a complex task. Now, the solution to this particular problem is to adopt a method which is called as a fast Fourier transform. Now, fast Fourier transform, it works on a divide and conquer basis, wherein a large block is reduced into small blocks the process continues. For example, n is broken down into n by 2, n by 2. N by 2 could be broken into n by 4, n by 4. We pursue this to the very smallest level. So this process of dividing is called as decimation. So the sequences are decimated either in the time domain or frequency domain. Hence we have two methods called as decimation in frequency and decimation in time. Now, there are other properties which are also exploited to make the computation faster. The fundamental method that we follow is called as radix 2 FFT. The meaning of radix 2 is that the value of the order will always be a power of 2. So we can say that n is 2 to the power of v, where v is a value which can range from 1, 2, 3 and so on. So powers of 2, we know the answer is 2, 4, 8 and so on. So if the expression of n satisfies this particular condition, then it is called as a radix 2 method. Similarly, if the number happens to be a power of 4, it is called as radix 4 method. Some properties of the Twiddle factor are exploited in order to make the computation of the DFT faster in the FFT method. The first property of Twiddle factor is called as symmetry property. The meaning of symmetry property is that Wn to the power of k plus n by 2 is equal to minus Wn to the power of k. This can be easily proved. First we take the LHS of the equation. Now the exponent can be split into two terms. So it becomes a product of Wn to the power of k into Wn to the power of n by 2. Keeping the first term as it is, as it's required in the solution, the second term expressed in the exponential form, e power of minus j2 pi by n whole power of n by 2. The value of n and n cancels, 2 and 2 cancels, and we get e power of minus j pi. Now we are aware that e power of minus j pi is cos pi minus j sin pi, which has the answer which is minus 1. Hence, we get the result as minus Wn to the power of k. This property can be easily tested. For example, if we consider n is equal to 4, on the complex plane, we know that there will be 4 points. The 4 points are corresponding to W4 to the power of 0, W4 to the power of 1, W4 to the power of 2 and W4 to the power of 3. We travel in the clockwise direction if it's a DFT. If we test the value W4 to the power of 0 plus n, in this problem n is 4, n by 2, we will get the equation as W4 to the power of 2 after simplification. Now W4 to the power of 2 is same as minus of W4 to the power of 0 in accordance to the property. Let us test this value. W4 to the power of 0 is equal to 1, whereas W4 to the power of 2 is minus 1. So if we travel a distance equals to n by 2 in the complex plane, the values will be similar, but they will have opposite sign. So n by 2 here means a half of a rotation on the complex plane for this example, where n value is 4. So we observe that the values 1 and minus 1. Similarly, at W4 to the power of 1, we have minus j. To that power, if I add n by 2, I get W4 to the power of 3, and we get the same value j, but the sign has minus. So minus and minus makes it plus. So this is a verification of the property. The next property is called as periodicity. Now, the Twiddle factor is periodic with a period of capital N. Therefore, Wn to the power of k plus n is equal to Wn to the power of k. This can also be proved in a similar fashion, splitting the exponent into two terms, Wn to the power of k into Wn to the power of n, keeping Wn to the power of k as it is, substitute for W of n in the second term. So in the exponential form, Twiddle factor is e power of minus j2 pi by n whole power of n, and n cancels e power of minus j2 pi. On substituting cos 2 pi minus j sin 2 pi, answer is 1. Therefore, the result is Wn to the power of k. Hence, periodicity property is also proved. In the example, once again, we can check for periodicity also. Now, the period is said to be equal to n. That means that W4 to the power of 0 plus 4, that is W4 to the power of 4, we actually come back to the same point. After we have calculated W4 to the power of 0, 1, 2, 3, W4 to the power of 4 actually happens to be the same point. So, Twiddle factor is periodic, having a period of capital N. Additionally, we could have a third property called as recursion property. The meaning of recursion is very simple. Wn to the power of 2 as an example could be expressed as Wn by 2. The rule is very simple. When you divide the power by 2, the subscript n should also be divided by 2. This could also be tested by substituting Wn to the power of Wn in the exponential form and verifying the answer. We have already discussed about radix 2 method. Under radix 2, n always happens to be a power of 2. If it is radix 4, it is going to be a power of 4. We have learned that how decomposition can happen for the DFT, and this method of decimating is something like a divide and conquer technique. Thank you all.